Well, thank you, Harvey. It's really a great pleasure for me to be able to give this talk in honor of Stephen Hawking's 79th birthday. And I want to talk about Hermann Minkowski's idea of space-time, which he introduced in 1908. Einstein in 1905 had introduced his idea of special relativity, but he thought of it in terms of equations and things like that, whereas Minkowski made it geometry. It's the four-dimensional geometry of space together with the extra dimension of time. So we have, imagine, say, three axes of space. These are the coordinates that you have, spatial coordinates, and then another axis to describe time. And this encapsulates the basic ideas of Einstein's special theory of relativity. Now, the important thing about Minkowski's picture is basically how light behaves. So we think of a light ray, which I have in the picture now. This is the history of a photon, if you like, a light ray, and it is tilted so that you picture it as traveling with the speed of light. In order that it doesn't sort of point completely along the floor, you have to have your coordinates comparable with each other. So the speed of light is something that it looks like, say, tilted at 45 degrees or some reasonable angle like that. Now, of course, there are lots and lots of light rays, and all the different light rays through the central point, the origin, will describe this thing called the null cone, which you see in orange here. And it's more important than the individual light rays, so let's remove that. It's more important than the axes, so we remove that. This cone describes the most important structure of space-time. It tells you how light behaves. Now, if we think of Einstein's general theory of relativity, then the space-time becomes curved. At each point, we have one of these null cones, and although this looks like a two-dimensional surface, you've got to imagine that it's really four-dimensional, and these little cones, actually, the little circle at the top of them, you think of as being a sphere, but don't worry too much about that. You can get away with thinking of the picture of 4 dimensions by visualizing a lower number of dimensions. Gets a pretty good idea of the picture. Now, these light cones can behave in complicated ways. At the central point of this picture, you imagine a flash of light, and that's the light cone as it goes out into space-time, and it's tangent to the light cones wherever it goes. But it can do weird things like crossing over. You see at the back of this picture, at the top right-hand side, you will see these light rays start to cross over, and you have a thing called a caustic and a crossing region where they cross over each other. And it makes it quite complicated, but it is important to understand something about the way these cones behave on these caustic regions where they cross over, and I'll come back to that later. It will be relevant to what I want to say. Now, in 1939, there was a paper by Oppenheimer and Snyder where they described the collapse of a spherically symmetrical dust cloud. Now, dust is a technical term which means matter with no pressure. And their picture, this is now a space-time picture. I'm not sure they drew a picture like this, but this is more or less what their description was. You imagine time going upwards. So you could take sections of this picture as you go up and up and up and up, and that would be the evolution as time evolves. And the cones you will see start tilting in strange ways as they go up at the top. Now, this picture was known, as I say, when they wrote this paper, and it does describe what we currently would think of as the collapse of a dust cloud to form a black hole. However, people, I think, didn't necessarily take it very seriously because particularly, well, first of all, you say the dust doesn't have any pressure. That's not really the important point. The important point is that everything is spherically symmetrical, so it falls absolutely radially inwards to this central point. And you'll see in the middle, you see this singularity, which is where the dust becomes infinite density because it's all focused into the middle. And people said, well, that's not very realistic because it might swirl around. It may not be completely symmetrical. It might have pressure. So why do we take this picture seriously? Well, in the 1960s, people started seeing things called quasars, well, they call them quasi-stellar objects originally. And they were very bright. They were brighter than, say, 100 or 1,000 times an ordinary galaxy's brightness, and yet they were pretty small. That's just to say, because they varied in brightness within periods of a few hours or a few weeks, which means that because of the speed of light would have to travel that distance, you would have to have something which was at least not bigger than something like the solar system. And to squeeze all that energy producing stuff in the middle of in single solar system means that you've got something like the kind of densities involved in the picture that you have here, the Oppenheimer-Snyder collapse. So people started to worry about whether something like this was going on, and whether, how does the energy get out? I mean, is there a radiation of some sort? And how does it get out if it just falls in radially? So people didn't take this picture terribly seriously, I think. There was, in fact, in the early 60s, a paper by Lifshitz and Kalatnikov in which they had claimed that in the general case, in general relativity, you would not get singularities. So this would imply that instead of falling into this central point, if you had irregularity, in a general case where you had not completely spherically symmetrical, but in a complicated kind of collapse, it might swirl around in a complicated way and come swishing out. So I think that was a common view that people had, that it wouldn't be, the spherically symmetrical picture was not realistic. So I began thinking about this. John Wheeler, I was working with at that time and somewhat earlier, and he was worrying about this problem, about what happens. I mean, is the Oppenheimer-Snyder picture realistic, or are the Russians right to say that when you swirl around, the thing will come swirling out again? And I didn't really know. I had a look at the paper that the Russians had written, and there was actually a serious mistake in the paper, which I didn't notice. I didn't see the mistake. What I did see was techniques which I was a little worried that they didn't seem completely convincing that these arguments would be utterly foolproof, and I wasn't really convinced one way or the other. And I remember walking in the woods and worrying about how you would characterize a collapse which had got beyond a point of no return. And well, let me go back a bit first, because I learned first about the picture I've just been showing, the Oppenheimer-Snyder collapse. I didn't see their paper, but I think I was in Cambridge in my second year as a research fellow, and I had a friend and mentor who was Dennis Sharma, who taught me a lot of physics. He was very influential in my understanding of physics. I was doing pure mathematics up to that point, and he suggested that I would go and listen to a lecture given in London by David Finkelstein. And David Finkelstein described the Schwarzschild solution. The Schwarzschild solution was the description of a spherically symmetrical body. It's the one that Oppenheimer and Snyder used, but not in the coordinates that they were using. The original Schwarzschild picture looked as though that you had a singularity at this place where the light cones start to tilt over and the light doesn't seem to be able to it gets sort of trapped at that place. It's what we now call the horizon. But people used to think of that as a singularity, because if you write down the equations in the way Schwarzschild did, you see that the metric, the description of how the light cones behave and so on, blows up. Things go to infinity and it doesn't make any sense. There were cosmologists, I think Lemaitre in particular, who had looked at this thing and decided that it didn't really, the Schwarzschild horizon, the Schwarzschild singularity, which is what people called that. This is when the radius became what's called 2m. M is the mass, and you use units where the gravitational constant is 1 and speed of light is 1, and all that's just convenient. And then this Schwarzschild radius, which would be, if you take the sun and squashed it down spherically symmetrically, then the place where it would reach this Schwarzschild radius would be a few meters. If you took the Earth, it would be, I don't know, about a centimeter or something like that. So it's very unrealistic for an ordinary star, or certainly for a planet. So people didn't really believe that these things would get that small. Nevertheless, there was work which showed if you have things like neutron stars or white dwarf stars in particular, then you do get trouble when they possibly collapse and they cannot support themselves. So people did worry about these things. And in fact, Wheeler and others, I remember Fred Hoyle and his collaborators were really wondering whether the Schwarzschild radius might be coming in and producing some horrible thing. So if you take the Oppenheimer-Snyder collapse, you see you don't get singular state there. It just seems to fall through until you get the singularity in the middle, but maybe that's not realistic because it would swirl around and do complicated things. Anyway, I remember walking in the woods and worrying about the thing that David Finkelstein had explained to me. And I'd worried when he explained it to me that you have this singularity apparently of the Schwarzschild radius, which is not a singularity. By choosing the right coordinates, you can sort of fall through it. And it's not a singularity, it's what we now call a horizon. Nevertheless, you still get the singularity in the middle. And it didn't seem that there's any way of getting rid of that singularity in the middle. And I wondered whether that was a general theorem or something. Is there a theorem which said if you had a very irregular collapse, did you still get a singularity? You seem to get rid of the one at the Schwarzschild radius, but can you get rid of it altogether? And I wondered whether there was a theorem or something of that sort. That was in 1958. And I really didn't know very much about general relativity. I started to think, what do I know about general relativity that other people might not know? And maybe that would be useful to me if I was going to try and prove something like this. And I thought, well, I know something about space-time, which is probably not very well known, which was the idea of two-component spinors. I learned about these from Paul Dirac, the great physicist, in lectures where he was describing quantum mechanics and then quantum field theory. And in the lectures in quantum field theory, I think this was the term which I went to in my first year as a research fellow, and he deviated from his normal course and described two-component spinors. Now, you see, Dirac was interested in spinors because he was very famous for having introduced the equation for the electron, which is called the Dirac equation. The Dirac equation uses what are called four spinors. They've got four components. And Dirac was, I think, aware that you could split them down into two-component spinors. But the two-component spinors were a little more primitive, but you needed two of them, if you like, two of the two-component spinors to make the proper Dirac equation for the electron. But he knew about the two-component spinors, and he described them in this lecture, which made them completely clear to me. I'd wondered about them before for various other reasons. And this picture that you see here is really a picture of a geometrical description of a two-spinor. On the left, you see the celestial sphere. So if you like, that's, well, it's either the past light cone, which goes out to infinity, that's the sky when you look out at the sky, or it's where your light rays go out into the future. It's the future sky, if you like. And so that's the celestial sphere. It is a real sphere. Now we're talking the right number of dimensions. Now, a spinor, two-component spinor, determines a single point on the sphere. So on the left, you see that point, and on the right-hand side, you see the little flag pointing out from the origin point, and the flag, where that little flag points, is the other piece of information you need to know how to describe geometrically what a two-component is. It has a curious property that if you rotate it through 360 degrees, it doesn't get back to itself. It goes back to minus itself. So you have to go twice before it gets back to itself. But that was a curious feature. And I knew about these things. I got familiar about them from Dirac's lectures. And I just thought, will these be any use in general relativity? I didn't see anybody use them before. Some people had, but not to my knowledge. And what I was rather surprised by was how it made the curvature much simpler than in the normal description. You could see that the curvature split nicely into two parts. One is called the Ricci part. That in this picture you see it causes light rays. I've got an observer at the top, and looking back, you see the light rays start to bend inwards. This is focusing due to what's called the Ricci tensor and Einstein's equations. The Ricci tensor is what the matter describes. So the matter density is described in Einstein's theory by the Ricci tensor. And the Ricci tensor focuses the light rays inwards in that way. The remaining part is what's called the Weyl tensor. And the Weyl tensor is, when you describe it in two-component spinors, it becomes a very, very simple thing. When you write it in tensors, it's a great mess. But in two-component spinors, it made a very simple thing, and I really could understand much better how it behaved. And it's important because it describes the free gravitational field. It is the analog. Maxwell has this wonderful theory of electromagnetism, where the theory has two things which compose compose it, there's what's called the charge current vector. So that's the charge and the current. And then there's the field, which is the electromagnetic field. Very important because you're seeing me through radio waves and things which Maxwell had predicted. So the electromagnetic field is described by the field tensor. And then the source is the charge current vector. Now, in general relativity, you have the analog of that. The field is the Weyl curvature, and the source is the mass. The Ricci tensor is given by the mass. And you can see in this picture how very differently they behave. So the distortion is what's given by the Weyl curvature, and that is really free gravity. Now, I want to move over to the next picture here. This is a picture in the paper which seems to have got me the Nobel Prize, which is the generalization I had of the Oppenheimer-Snyder picture. You see, it really is the Oppenheimer-Snyder picture, but I've now drawn it a little bit more carefully than the one we had before. We see the dust cloud collapsing inwards at the bottom of the picture, and time going up the picture, so it falls inwards towards the center. Now that is, if it's spherically symmetrical, that is the Oppenheimer-Snyder picture. Now I was interested in what happens if you wiggle this picture, that is, if you have the matter not really completely spherically symmetrical, but something irregular. Do you still get this nasty thing in the middle where the curvatures go to infinity, and it's called the singularity, and people don't like the idea of the singularity because your equations simply give up at that point. Now, is this going to persist, or when you have a general complicated collapse, does it sort of wiggle around and come swirling back out again? Well, what I thought I'd been walking around, well, it was in a later conversation I was having with somebody, with Ivor Robinson, and I had this idea of a trapped surface. Now, you see in the middle of this picture a little ring. This ring is going round the matter. It's surrounding the matter, but just a little too late because it's got inside the horizon. The horizon is described by this cylinder that you've seen going upwards to the top. That is where the light cones start to point inwards, and light can't escape from inside that region. Now, if you have this trapped surface, which is the little ring going, I call it a trapped surface because, although, as I said before, the picture is you're losing a dimension. And that ring looks like a little circle where it's really a two-dimensional surface because you've got to have an extra dimension. But don't worry too much about that. The point about it is that you could imagine a flash of light on that ring. And as that flash of light, what's its history going to be? You can see that its outward part is falling inwards as well as the inward part. So let me move on to see what this is. Here I have an element of that. The bottom is a little, now I've drawn it as a two-dimensional surface. So we see that little element of the surface, and the flash of light, there'll be an outward flash and there will be an inward flash. The outward flash is on the right, moving up to the right. The inward flash is on the left. And the history of that is the cone that you see. So that the little flash of light, I'm trying to draw two dimensions in the space-time at the same time, so it's a little confusing, the picture, I'm afraid, but that is the picture of what a little flash of light would do. Now here is what a trapped surface would do. Look at the top left of the picture. Here we have a little piece of surface. It's an ordinary two-dimensional surface. You imagine a flash on that two-dimensional surface all over it all at once, and if it's bending on the concave side, it will, flash of light, the rays will be converging. On the convex side, they will be diverging. Now, that's the normal experience. On the right top, you will see what I'm picturing a trapped surface would be like. On the one side, they're converging, and on the other side, they're converging. And that's just what you get on this trapped surface. And if you wiggle it a little bit, that will still be true. So it's a sort of what you call a stable property. You can change so that the geometry is not spherically symmetrical. It could be quite complicated, but close to being the picture that I showed you before, but not like it really could be significantly different. And you could imagine as the material falls inwards to the center, that the differences will get more and more, and the swishing around gets more and more complicated, so it could easily, you could imagine, swirl around and come out again. Now, you might think this is a very strange thing to have the light rays converging on both sides. It's not really all that strange. On the bottom of the picture, you see a general case where this can happen. I thought of 2 points in space-time, and these are their past cones, and their intersection. You've got to imagine to get the dimensions right, that's really a little piece of a surface as they intersect at the bottom, and the light rays will be converging on both sides. What's strange about a trapped surface is not so much that the light rays converge on both sides, but they do this at the same time as the surface being closed in on itself. And that's what I call a trapped surface. Now, what I considered in this situation is the future of that trapped surface. So in the picture I showed you a moment ago, we had the shaded in the region to the future of that surface. What do I mean by the future of that surface? I mean that all the places you could get to without exceeding the speed of light. So that's the future of that surface. All the regions of space-time that you can reach without exceeding the speed of light. Now, what's the boundary of that region going to be like? Well, you remember on a very early picture, I showed you what the light cone of a point did. It started to cross itself, and you get situations like this in this picture where you see the light rays start crossing each other, and it's really a nuisance if you want to have to think about that. But the key point of it is that you don't have to. You need to know that the light rays start to converge, and you get these things called conjugate points, that thing in the middle there. And once you find a conjugate point, you've known it's gone at least as far as where these light rays start crossing each other. And so you have to stop off before that happens. So what you get is something a little complicated in its shape as the boundary of the future of this surface, but it doesn't have all these complicated caustics and crossings. Well, I mean, you do start to cross, and when they cross, then that's the end of the boundary. So I can't go into the details of this, but it was a useful thing to think of, and it enabled me to produce this theorem, which showed that as long as the energy does not go negative, that is, that when the rays start to focus, you remember I had this bundle of rays focusing inwards by the Ricci tensor, and the thing is that when you have positive energy, this can distort it, but it can't stop the inward focusing. It's got to get what we call a conjugate point to the point which the observer is looking from. And it was this feature that you have to have a boundary. You have to have a boundary of the future which is compact. It's what's called compact. It means it's sort of finite in a sense, and this compactness is inconsistent with having a surface of evolution which is sort of non-compact. You imagine that the collapse to the black hole takes place with a very, very large region, so we can call that non-compact. It's just a very big region, and this region essentially goes out to infinity, and that collapses inwards to this thing which you can sort of focus back or project backwards to your initial surface, or your Cauchy surface, as it's sometimes called. And that Cauchy surface, you've got a finite region, which is a compact region in this non-compact space. And that's a contradiction. I don't want to go into that argument, but that was the argument which my theorem depended upon. Now, I gave a talk about this in, I think it was in 1964, at King's College London. And in the movie, you will see me giving a talk, like, it's not me, but somebody like, supposed to be me, giving a talk about this theorem. And you see in the audience, there's Stephen Hawking with sparks coming out of his head, getting inspired by this talk. In reality, he was not there. However, it wasn't so bad, because my colleague, as I mentioned, Dennis Sharma, who was very important to me in the history of my understanding of physics, he heard about my lecture in London and decided to have a repeat in Cambridge. And Stephen Hawking was at this repeat in Cambridge, and he heard the techniques I was using in the talk, and then I had a private session with him and with George Ellis, possibly Brandon Cartwright. No, George Ellis was there. And the three of us discussed the techniques that I was using, and in quite a lot of detail. And Stephen picked up on this. And initially, he very quickly used my theorem in a way I hadn't expected. You see, I was thinking of using it as a local collapse to show that the black holes produce singularities. And he thought of it in a different way. He was thinking of this describing the whole universe. So you're thinking of a universe which is non-compact, so it's not closed spatially. You must say it's going out to infinity, and he could use my theorem, but in the reverse direction in time. The arguments don't really depend on which way time is going, so you can use them one direction or the other direction in time. What was surprising to me about his use of this was to use it as infinity rather than for a local argument. And yes, you can use the same argument to show that in a cosmological situation, if there is enough matter around to cause the light rays to converge, way out. Now you're not talking about a local collapse. You're talking way out at what's called the sort of horizon that you see, and the light rays may start to bend inwards at that point. And so this was his argument. I was very impressed by how quickly he'd found this. Now, one of the troubles with this argument was that it depended upon the universe being spatially non-compact, and it might be compact. That is, it might actually close up in itself spatially. And so Stephen started thinking of generalizing these arguments in ways which did not depend on that, did not depend on the Cauchy surface. I should say a little bit more about a Cauchy surface. You see, usually in physics, what you do is you try to predict the future. So you know what's happening, say, at a particular time. And then if you have enough information on that time, you can evolve using your equations to see what happens in the future. And this surface is called a Cauchy surface. And you've got enough information so you can evolve it to tell you what's going to happen in the future. So Stephen Hawking introduced this idea of a Cauchy horizon, which is this thing with the H plus of S, which is the Cauchy horizon. And he looked at the structure of the Cauchy horizons, and it's very much like the boundary of a future, but the other way in time. And so you can use very many of the same techniques that we were using before to talk about Cauchy horizons. And this enabled him to generalize the arguments that I'd been using and to dispense with the notion of a Cauchy surface. I thought this was a really important development, and certainly when you're talking about cosmology. And so Stephen had 3 papers in the Royal Society using these techniques, and then we had another paper finally together, which we wrote, which generalized more or less all the theorems that we had before, which with a major contribution due to Stephen in this, which I think certainly one of the most important things he did. I'll come to one of the other most important things he did in a moment. But first of all, you see, he was more interested really in the Big Bang and in was that a generic phenomenon, or might have there been a bounce of some sort before, some previous universe which collapsed and somehow swirled around and came out again. And lots of people had pictures of that nature. Or was that necessarily a singularity? And that what one seemed to conclude from all this is it was necessarily a singularity. Now, I want to say a little bit more about this picture. This is a picture, basically, the standard kind of cosmological picture that we have. You see at the top part of the picture, this exponential expansion. This is, well, various things got the Nobel Prize. This one with the observations of the distant supernova stars, of the expanding exponential expansion that you start to see at the top part of this picture. So it starts to bend outwards and expand exponentially. At the back, you may see some rather frizzly. It's not quite clear what's happening. That's deliberate because I don't want to prejudice this as to whether the universe is actually open or closed. So it might close up on itself, or it might really go on forever. I don't care in what I'm going to say here because it works either way. But it's useful to pretend that it closes up at least for a bit, because then I can draw the pictures more nicely. Now, what does current cosmology say about the Big Bang? You see, I kept worrying about the uniformity of the Big Bang. I'll say a little bit more about that in a moment. But the Big Bang is not a really very generic situation, and it's very smooth. And cosmologists like to have a look to see what's going on in the very early universe, and they introduce this idea of inflation. Inflation is described in this picture. What do you see in this very powerful microscope, or magnifying glass, which I've shown? What you see, according to current cosmology, is this inflationary phase, which looks like the exponential expansion of the remote future, but another one, which was supposed to have taken place in, well, 10 to the minus 32 seconds, a ridiculously tiny fraction of a second. Now, that ridiculously tiny fraction of a second, I never really took it seriously. It seemed to me it was, you had to introduce this strange inflaton field in order to make it work. And I didn't really think it did work for the reason which I'll come to, because, well, you see, this is the picture we had before, and you imagine that inflation is supposed to smooth everything out. It does other things which are more respectable. But the smoothing out of the universe, I never really thought that it worked. Why did I think that? Well, think about the time reverse of this picture. So now it's a collapsing universe, and the universe is now collapsing, and it could be full of all sorts of black holes and things which cause a great big mess. You don't expect to see this very nice singularity at the top. You see a huge mess. That's the most likely thing you would see, something much more like this picture, where you have black hole singularities all messed together and fusing a very, very general singularity. And so I thought, well, if inflation is supposed to get rid of the mess like this, why? You see here, inflation doesn't do anything. It doesn't change the picture at all. When you get curvatures this great, the inflaton field does nothing. So why did you not get a universe which started like this, completely different from what we do see, with the Weyl curvature going completely wild, as in fact the Belinsky, when I said Lifshitz and Kalatnikov, Belinsky found I think it was Belinsky, who found a mistake in the paper. When corrected, they found a much more general type of singularity, which could really be a generic singularity, the kind of mess which I'm trying to describe in this picture here in some kind of schematic way. But nothing like the very smooth picture that we really seem to see for our universe. And I kept wondering about this. Why on earth is it not like that? Why is the universe not one of these very complicated things? And I remember thinking about all the different kinds of collapse singularities you can have, and cosmologists never thought about these. And I remember seeing James Peebles, who was the winner of the Nobel Prize last year, and he had done amazing work on the first 380,000 years of the universe existence, and we know a lot about that. And I said, why don't you consider these more complicated things? And he looked at me and said, because the universe isn't like that. And that made a big influence on me, because I thought, my gosh, it's not like that. And then I thought, why on earth isn't it like that? It's really a hugely important factor, which is very deeply connected with a thing called the second law of thermodynamics. You see, there's something very paradoxical, because when you go back to 380,000 years after the Big Bang, which is when you start to see light coming out, that's called the last scattering surface or the decoupling surface, not quite the same, but they're almost the same. And that is what the light you actually see coming from there. And it is very, very uniform. I think that's what James Peebles was really saying, is that we have this evidence that the universe is extremely uniform, way, way, way back as far as we can see it. And not just that, you see from the spectrum of the frequencies that we see that it is what's called a Planck spectrum, which means it's maximum entropy. And I thought, this is a paradox. You're going back and back and back and back in time. And according to the second law of thermodynamics, the entropy, that is the randomness, should be increasing. And you see the very earliest thing you directly see, you see randomness as a maximum. That is this Planck spectrum, which is telling you that the entropy is at a maximum. Now, in this picture here, I've got in the top three pictures the normal sort of picture people have of entropy increasing. Let's imagine a gas in a box. And we have a little smaller box, which is containing all the gas originally in the bottom. I'm talking about the top left picture. I'm talking about the bottom right part of that top left picture. And we've got all the gas trapped in the little box. Now you open the box and let the gas spread out. So as entropy increases, the randomness increases, you see the gas spreads out more and more uniformly through the box. And that is the normal picture we see of the second law. But we see in the actual universe, way back at this 380,000 years after the Big Bang, you see the top right-hand picture, and we see the bottom left-hand picture. Now, the bottom left-hand picture is what you see for gravitating bodies. What I'm trying to illustrate here is the very extreme difference you have between a gas in a box and gravitating bodies. So imagine those as stars or something like that. And as they evolve in time, with entropy increasing, they get more and more and more clumpy. And they get black holes, right? At the end, you get black holes where the entropy absolutely rockets up hugely. Even right now, in our current universe, by an absolutely enormous figure, the entropy is almost entirely in black holes, according to the famous Bekenstein-Hawking formula for the entropy in a black hole. So what we're seeing in the very early universe is this very curious imbalance between matter, top right, gravity, bottom left. So that the matter is uniformly distributed, but when I say gravity, bottom left, I mean that the gravitational entropy is at a minimum. And I'm really puzzled about this. There's something very, very odd about the Big Bang. It is completely random as far as we can see, pretty well completely random as far as the matter, and completely unrandom with regard to gravity. So we have to have a theory which is imbalanced in this very strange way. Now, people try to say, well, how do you describe the singularities? Well, the singularities are where quantum gravity comes in. You see, you've got to have the quantum mechanics starts coming in when the curvatures, the radii of curvature become, well, what's called the Planck length, or the Planck time is 10 to the minus 43 seconds. I mean, ridiculously tiny scale. So you've got curvatures absolutely huge because the radius of curvature is absolutely tiny. And so then quantum mechanics would come in, and so who knows what goes on. That's the sort of picture people have. So I thought, well, whatever quantum gravity is, it must be a very, very peculiar theory. It must be very completely time asymmetrical, because it gives you, in the remote future, these black holes, this bottom right of this picture here, and in the beginning, you see bottom left of the picture here. And why does quantum gravity give you this huge imbalance? And so for many, many years, I puzzled about this, and I couldn't make sense of it, until I started to think about infinity a little bit more. And let me try and describe this Escher picture. It's a very beautiful way. He has these, I think there are 5 different pictures describing the infinity of what's called hyperbolic geometry. Don't worry about the geometry. What we're going to worry about is the infinity. These are this is the first of Escher's circle limits, and you see these fish creatures. I'm going to point out particularly their eyes, because they're exact circles. And as they get smaller and smaller towards the edge, their eyes remain exact circles. In fact, the angles on their wings, or whatever we call them, the fins, are the same right towards the edge. What this means is that the geometry right out to the edge is the same if we think of it as conformal geometry. Now, what is conformal geometry? See, normally you think of Euclidean geometry, you talk about distances, sides of lengths of angles. You have a triangle and you've got the lengths of the sides, and that's part of Euclidean geometry. But if we just talk about the angles, then that means you don't think about lengths. And this is conformal geometry. It's a very beautiful kind of geometry which generalizes the Euclidean notion of geometry. And here we have this thing called hyperbolic geometry, and the whole of it is depicted in this conformal picture. So the fish in the middle, as far as they're concerned, are just the same as the ones way out towards the edge, although it gets very, very crowded towards the edge, and you look as though they look to us as though they're very small. As far as they're concerned, they're just the same as the ones in the middle. Their conformal geometry is the same as the conformal geometry in the middle. So what's nice about this is with these pictures, you can describe infinity as a place. So if you are only interested in the conformal geometry and not just the sizes of things, the shapes, if you like, the shapes of small things, then you can squash the infinity down and think of it as a boundary. And that's what I want to do to space-time. So this is what I'm trying to do in the next picture. The conformal geometry in space-time is described by the light cone or the null cone. You see, if you want the metric, then you've got to put these surfaces which tell you distances. How is it distances? Well, we imagine particles zipping along, and when they heat, it's really times. It's times which define the metric. And they encounter these little bowl-shaped surfaces at the top or the hill-shaped ones at the bottom. And what determines where those things are? Well, it's the 2 most famous formulae of 20th century physics. At the top, we see Einstein's E equals mc squared. At the bottom, we see Max Planck's E equals h nu. Put them together, that tells you that the top one tells you energy and and mass are equivalent. The bottom tells the energy and frequency equivalent. That both together tells you energy and frequency equivalent. So any massive particle, I should say mass and frequency are equivalent. So any massive particle is a clock, a very, very perfect clock. And there's what this described in the picture. The surfaces are there when you have mass. What happens when you don't have mass? Well, a photon doesn't even see the surfaces, doesn't experience the passage of time at all. So as far as the photon is concerned, we don't even have the metric. You have the conformal structure. So if you have massless things, you're only interested in conformal geometry. If you're only interested in conformal geometry, then you can squash down infinity, and you can do it with a nice space-like surface. So it's like a time, if you like. It's time infinity. And that happens because of the cosmological constant, which was introduced by Einstein. We have here the introduction of a cosmological constant, which gives you the exponential expansion, but that enables you to squash down infinity to have this space-like infinity, which you can squash down to a finite boundary. What about the Big Bang? Can you stretch it out? Well, my colleague Paul Todd said this is a much nicer way of saying that the Weyl curvature, see, I was trying to say, well, quantum gravity in this funny way makes the Weyl curvature zero. Forget about quantum gravity. Maybe the Weyl curvature is zero. That's just a hypothesis. Paul Todd's way of saying it was, okay, let's say you can stretch out the Big Bang to make a nice finite boundary. That's fine. It's a very nice description that you can make both the infinity in the future and the Big Bang infinity of density in the past, make it a finite boundary. This is the crazy thing. This is my picture of conformal cyclic cosmology. The Big Bang had to be without any Weyl curvature because it was the continuation of the remote future squashed down of a previous eon. So each of these look like universes on the left. They're what I'm calling eons. The one in the middle, think of that, that's us. Our Big Bang stretched out becomes the squashed down remote future of the previous eon. Our remote future becomes the Big Bang of the next eon. Is this something, just a crazy thought that you can't experimentally think about? Well, you see there are signals that can get through. This is representing the join of one eon to the next. I'm thinking of light rays getting through. They certainly can in this picture. Can you see anything which gets through? What else could get through? Well, black hole collisions could get through. So the bottom picture, sorry, in the middle picture, I have a surface that's meant to be the crossover between two eons. In the bottom half of this middle picture, we see black holes coming together, bang, 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 running into each other, the gravitational waves coming out. The top of the picture is us looking back to the stretched out Big Bang, and we will see these little rings, which are concentric rings coming from the Big Bang, bang, bangs like this. Well, do we see them? Well, this here is a picture of the Planck data. These two satellites, one was called the Planck satellite, and the earlier one was called the WMAP satellite. This is the Planck data from the Planck satellite, and my colleague Vahe Gurzajan plotted the centers of triple concentric rings of low variance. This is the prediction of the theory that you would get these. And the remarkable thing about this picture is that not only do you get this very clumpy distribution, which says something funny is going on, but you get them clumpy in the color too. Now, what does that mean? The red ones, the color coding tells you, according to the theory, that they're very, very distant, even outside what's called our particle horizon. The blue ones at the top are much closer. They're within our particle horizon, according to current cosmology, but they are super duper clusters of galaxies or something. If you're going to explain this picture, you've got to have some theory which explains why the universe is in this description. These are observations, complete just observations. You see this using a particular way of analyzing the data from the Planck data, and you see this very curious inhomogeneous distribution explained in the theory I've described by there being huge lumps of concentrations of materials in different places. And what about this? Now, this is the Hawking evaporation of a supermassive black hole. That's why I said I would get around to this. This is the Stephen Hawking's really most important contribution to the whole of the subject. And here we see a black hole evaporating away. we don't just get the Oppenheimer-Snyder collapse. If you wait long enough, and it could be a huge length of time for the most massive of the known galactic clusters, who expect supermassive black holes, which would take something like 10 to the 100 years or more than that. That's 10 to the power 100. Sorry, 10 to the 100 years, something like that, for them to disappear. More than that, probably. And they disappear with a pop at the end. You see all the mass of that black hole goes out in radiation. And you might say it's all lost. But in the conformal picture, it's not all lost. You see, this is a picture from a paper written by Christoph Meissner, Pavel Nurowski, and myself. Came out about 6 months ago, or a little bit more than that, I think now. The bottom horizontal line represents the crossover, according to the theory. Now, maybe there's some other theory, but the crossover is the join between the previous eon and our eon. So that little point called H, that's what I'm called a Hawking point. Why I'm calling it a Hawking point? Well, because the little line leading up to it from below it is meant to be the history of a supermassive black hole. And all the radiation of it, remember the Escher fish, when they get close to the edge, it's all concentrated in a little tiny point. So the entire radiation from that supermassive black hole comes through in that little point. It now spreads out through the 380,000 years that James Peebles was talking about to the last scattering point, or the decoupling point. It would be spread out to a radius of about 8 times the diameter of the moon. And so we would, according to this theory, expect to see spots in the sky which are something like about 30 times or maybe 50 times the average variations of temperature in the cosmic microwave background. Do we see them? Yes, we do. We see several of them. We see at least 6 of them, which are seen in exactly the same places in both the WMAP and Planck data, in exactly the same points. Apparently nobody has seen these spots before. Why? Probably because they've never looked, because they think that inflation eliminates these signals completely. But we see them, and in this paper, Christoph has this very clever way of doing analysis, and the analysis tells us that these points are there with a 99.98% confidence level. So that's a very strong confidence level, that these spots are there. Exactly where they are, we don't have such a great confidence level, but the fact that these 6 points are seen both in exactly the same places in the WMAP and the Planck data, I think is strong reason to believe that those are actual Hawking points. I think this is an indication that a lot more study has got to be put into this. I'm not saying that these are necessarily actually Hawking points. I think they must be. I can't think of any other explanation. It's certainly not part of the inflationary picture. The inflationary picture should wipe these things out completely. I have no idea how it could be accommodated within conventional cosmology. I would be very intrigued to see an explanation for these spots in any other theory than the one I've been putting forward. So that's the story as it stands at the moment, with the singularities in black holes and the singularity at the Big Bang, and what is the nature of them and how do we understand singularities. It's a big question for the future. How does quantum mechanics combine with general relativity in the appropriate way? And I think these issues are things that we will be interested in and will confront science for many years to come. So thank you very much. It's been a great honor for me to be able to give this talk.
Okay, well, thank you, Roger, for your fascinating lecture about black holes, and apologies for the technical problems that we seem to be having at the moment in trying to get Zoom to work properly. Now, remember, it's possible to ask questions about the lecture using the Slido site. So before we go to those questions, I thought I'd start by asking some questions that occurred to me when I was listening to your lecture, Roger. So what struck me when you were describing your singularity theorem was that the way you described it was very visual. And so I was wondering, was this the way that you discovered the theorem? Did you visualize how light rays emanating from a trapped surface would have to behave before you sat down and worked out the mathematics?
Depends what you mean by mathematics. I mean, it's certainly getting a feel for what boundaries of futures look like. You see, I'd worked out a lot of that from another problem I was thinking about, which had not to do with black holes at all. I was looking at a problem about asymptotic gravitational radiation, if you like. And I had written a paper for the Royal Society, which actually came out almost at the same time as the black hole paper, because the black hole paper came out much more quickly because it's physical letters. But the other one was about how zero mass fields, including gravitation, behave in the asymptotic limit. And one of the problems I ran into there was the shape. You have this geometrical way of looking at infinity, which was very useful in order to answer questions like what happens to what happens to gravitational radiation and what is radiation, and you like to go out to infinity, and usually people do this by complicated analytical procedures, and I much preferred to do a conformal transformation which brings infinity into a finite place. You could just look at it, and the problem was whether infinity had the right sort of shape. I won't go into the details of that. But I ran into a problem, and in order to solve this problem, it wasn't really important for the paper, but I really needed to clarify it for myself. And I put an appendix in this paper, which had to do with, roughly speaking, the shape of infinity. And the techniques I used for that were very much what I needed to use in the black hole problem. So I had these techniques more or less at hand. I didn't know quite how to use them in the black hole problem, but when I had the idea of a trapped surface, it did not take me long to realize that the boundary of the future of that trapped surface would be a compact region, and that there was some contradiction involved in mapping that back into the initial surface. So it was having that experience with my other paper which gave me the understanding I needed. Now, how much is that visual, is your question? Well, a lot of it is visual. But to what extent is it's visual and analytic at the same time? I mean, you have to know what to trust in your visual pictures and what not to trust. So it's not there's not a clear division between these things. But certainly I think about things in a very visual way. That's certainly true, yes.
Good, thank you. So a second question is that your theorem tells us that singularity formation is a robust prediction of general relativity, but to conclude that the singularities must lie inside black holes, you had to introduce your famous cosmic censorship conjecture. I was wondering if you could just say a few words in trying to describe that conjecture in general terms for our audience.
Well, you see, in fact, the Nobel Committee was rather generous to me in a way, because my contribution did not actually tell you that black holes were a robust prediction. What it did say is that singularities are a robust prediction. Now, the thing is that I suppose the natural thing to expect is that these singularities are hidden in black holes, but it's not a theorem. It's not a mathematical conclusion that one can necessarily derive. And in the paper I wrote, which has a lot more in it than the paper that apparently got the Nobel Prize, there was one that I wrote for the Italian journal, and Nuova Cimento, who was a special issue of that, was a conference. But anyway, I did raise a lot of questions. Part of it was how you get energy out of black holes and things like that, the rotation of a black hole. But the question I raised right at the end was, is there a theorem or some general principle which tells you that these singularities that you could see directly, a naked singularity, would be one from which information could come directly out of the singularity and not being shielded from vision by the horizon? So in a way, you see, it's not the horizon is the clothes, and if it's naked, it doesn't have any clothes, you see. So it would really be cosmic censorship was the censoring that you didn't have these singularities you could directly see. Now, I was quite open-minded about that. And in fact, a paper I wrote later I'd actually explored the possibility you might have naked singularities. And this was the one that led to the thing called the Penrose inequality, because it was a condition which showed that if you could violate this inequality, then you would have naked singularities. And I didn't prove that you couldn't violate it. That was the Penrose inequality was a conjecture. I did not prove anything. It was quite curious because Stephen Hawking regarded it as a convincing argument that naked singularities didn't exist, because I had failed to prove that they did exist or something like that.
Excellent. Maybe I should ask a question coming in from our audience. So I have a question here from Sunak Chakraborty, who's in India, who asks, will an observer falling into a black hole be able to witness all future events in the universe outside the black hole?
The answer to that is no. I mean, if I just take the standard Oppenheimer-Schneider model, which is spatially symmetrical, then you can see if you take one of these time-like curves which end on the singularity, its path is a very definite region, and it certainly does not see the whole of the universe. It's a very explicit part of the universe you see. And I would imagine that's the general case. So you would certainly not expect to see the whole of the future of the rest of the universe. No, very far from it.
Okay. Another question by someone called Vicky from Hungary, who asks, can a black hole fully evaporate through Hawking radiation? If not, what is its long-term fate?
Well, of course, there are unknowns about this, but my expectation is, yes, it would evaporate away. You see, the question is what happens at the very last moment. And I tend to call this the pop, which happens at the end, because it's relatively small. There is this event when the last moment of the black hole's existence, and the amount of radiation, the intensity of the radiation increases as it gets smaller. It gets hotter, I should say, and it gets very, very hot and infinitely hot right at the end. But I'm not. What was the question exactly? I can't quite remember the
question was: can a black hole fully evaporate through Hawking radiation? So,
well, you said. I mean, yes, would be the answer.
Good.
Of course, there's unknowns about what happens at the very last moment. And of course, you'd expect at the very last moment your black hole has got down to maybe something like a Planck scale, which is a few grams, or 10 to the minus 5 grams, I should say. And no, it's 10 to the 5th. I've got it the wrong way around. How many grams is a Planck mass? Anyway, whatever it is, it's quite small, but not infinitely small. But nevertheless, one can start questioning what happens at that point. But almost the entire black hole has disappeared by then, so why not the whole thing? Sure, the whole thing should probably disappear completely, yes. Into radiation.
Yes.
The radiation is there.
We just mentioned Stephen Hawking, and we're celebrating Stephen Hawking's birthday today. So you were a collaborator with Stephen and a lifelong friend of his. So I just wanted to ask you about Stephen's most important contributions to physics. So in your talk, I think you mentioned Hawking radiation, and we just discussed that. And that this effect is such a big discovery that sometimes it tends to overshadow some of Stephen's other work on black holes. So I wondered if you could tell us briefly what you think.
He did.
Yeah, what do you think was Stephen's
the most important thing? Well, a clear formula for the entropy in the black hole. It's all part of the same problem. I mean, Eckenstein had a rather slightly hand-waving argument to suggest that the area of the black hole, the area of the horizon, was a measure of its entropy. And Stephen had a much clearer argument to show with a factor of a quarter, which told you more or less, well, exactly what one would expect for the entropy of a black hole. And I think that all goes along with his the Hawking evaporation, Hawking radiation. So that's all one story, if you like. And I regard that as his most important contribution. He did do other significant things with black holes. One of them had to do with the asymptotic behavior of a black hole. And we're thinking classically now, not to do with the Hawking evaporation. But you see, a black hole might be irregular. I wouldn't expect it to be exactly like the Oppenheimer-Snyder picture. It could be with some irregularities, but it may very rapidly radiate away, and you end up with, well, the sort of thing you get is the Kerr solution, so it would be rotating, and that has a sort of stability about it. Now, the question was, is the Kerr solution this limiting, or is it unique as the kind of stationary black hole that you could get at the end? And it was really Brandon Carter who started. Well, go back a little bit more than that. It was Werner Israel who, for the non-rotating case, he was looking at what static configurations could you have with black holes, and it turns out to be the Schwarzschild solution, that all the other moments will there was a period of time when people believed that somehow that shows black holes didn't exist because you could only have the spherical ones. So what happens to all the unspherical ones? But the point is that all the irregularities get radiated away. The quadrupole, everything up to the quadrupole moment, including that, disappear in radiation, and you're left with just the static Schwarzschild solution. But if it's rotating, then you can also have the Kerr solution. And Brandon Carter started this. There were several people involved, David Robinson and Stephen. You see, the thing is, the work before that was to show that if you had axisymmetry, then it had to be the Kerr solution. And what Stephen showed by a rather general argument, which was a genius argument, more or less showed that you had to have axisymmetry in the limiting case. So that was an important contribution to this whole discussion.
I guess that there was also...
What else to do with black holes? Oh, sorry, go ahead.
So there was the area theorem, or I guess was one of the...
Well, there's a little bit of a question about that. I mean, the story there, I've never got to the root of it, and I don't quite know what Stephen thought about it. You see, there was a story there. I was visiting Cambridge, and I remember having quite a long discussion with Stephen in one of the lecture rooms. And I was describing to him this general tendency for the area to increase, and that this was a general result. And he didn't seem to know that at the time. I can't remember whether my paper with Floyd was out by then or not, but certainly we'd done this work. And then I was staying in Cambridge, and the next morning I got a phone call from Stephen, and he said that this result we were talking about the previous night, he had an interesting idea about it. And he said, oh yes, what was that? Suppose you have two black holes, and they collide, and you can get, from using the area, the fact that the area cannot decrease, is you get a limit on how much radiation comes out, something like that. And I remember that was a remarkable idea. And I said I'd never thought of doing it that way. And how that you could think of the area of the black hole as being a composite of two different black holes together. So that was what he did. Now, his later memory of what happened was somehow that his memory was different from mine, you see, because I did talk about this theorem to him already the night before. But then he had this inspiration when he was waking up in the morning or something, I can't remember what it was. And that I took to be the fact that you could apply this result to a pair of black holes. And you could get a limit on how much radiation could come from a pair of black holes. But then it became this area theorem, as he was starting with, as his greatest contribution, and I was very puzzled about. Sorry, let's stop this story and go on to the next question.
Of course, that limit on how much gravitational radiation you can get is quite relevant now that we're observing gravitational radiation from black hole mergers. Just another very quick... No,
that's right. It would be relevant to that, yes.
Yeah. Yes. Another very quick question is there a maximum size limit for black holes?
No, except there's a limit to how much matter there is in local regions in the universe, I suppose. No, there's no theoretical reason they can be as big as they like. Mm-hmm. I mean, big ones can crash into each other and make even bigger ones. Depends on how much is available. I mean, if there's no matter around, you can't do much with it. But there's no theoretical limit to the size of them.
Another very quick question, I think we've only got a minute or so left, is in your lecture, I think you mentioned Paul Dirac and spinors. I was interested because
Yes.
Paul Dirac, a former Nobel Prize winner who discovered the equation governing the electron, he was at St John's College in
Indeed.
Cambridge at the same time as you. So did you have any interactions with
Yes,
Paul
indeed.
Dirac?
Oh, yeah, quite an important one, you see. More than once, but the main one was, I remember being opposite him at dinner on one occasion, and I said I had some ideas that I wanted to discuss with him, and so I had a conversation with him in the lecture room about the spinor description, how you can write the curvatures in terms of spinors, and that I pointed out this equation that you have on the viral spinor is this very symmetrical object and looks like a massless field, and the question was, was this any use for quantization? And his remark was, well, you have to have a Hamiltonian, you see. Well, that's just... No, he was very interested because he gave a recommendation for me when I went to my job. I guess I had a job in the University of Texas. And they showed me the recommendation letter I had from Dirac, and it was very short, but it was coming from Dirac. He said, you know, it was based on this conversation where he said that I had done this interesting thing, and it was all my idea that I developed. And I suppose that was a nice recommendation to get from a man like Dirac, certainly.
Yes.
But I've had other experiences with him too. Some of them not quite so good as that one. There was an occasion when I'd written a review of his book, which is a very nice book, very compact book, and he got something not quite right, you see. It was to do with whether the energy was localizable in a gravitational wave. I said, well, actually, it isn't quite true. And he didn't normally talk to people, but I was at some reception, and I was one end of the room, and Dirac was at the other end of the room. And he saw me, and he came walking up to talk to me, and he complained about what I'd said in the recommendation. And I said, well, look, the energy isn't localized in a gravitational wave, and I explained why. And then he went away again, so I guess he must have agreed with me at that point. But he was somebody who didn't like to be wrong. So if he said something which wasn't quite true in his book, which he did in this case, and I pointed it out in the review. And so I guess he felt a little uncomfortable about that. That was only a very, very minor point, but it wasn't, what he said was not quite correct, that's all.
Everyone makes mistakes, even Nobel laureates, I guess.
Oh, yeah, even Dirac. Not often, but still. Yes.
Okay, well, this has been really interesting, but I'm afraid that's all we have time for today. So thank you very much, Roger, for answering our questions.
My pleasure.
Personally, I must say I found your description of the history to your Nobel Prize winning work in your lecture absolutely fascinating. And I've also enjoyed greatly hearing your reminiscences of working with Stephen Hawking. So thank you again, Roger, for being with us this evening and letting us know about your exciting work on black holes.